Imagine for a second that you cross a threshold in space, and suddenly turning around to go back the way you came is no longer a physical direction.
Right. It just ceases to exist.
Yeah, it becomes an impossibility. And not because your engines aren't strong enough or, because you're caught in some invisible tractor beam.
No, it's because the universe has contorted itself so violently that the direction of backwards has literally become a journey into the past.
And since you can't travel back to yesterday, you can't turn your ship around.
It completely violates our biological, intuitive mapping of reality. I mean, we're used to 3 dimensions of space where we have total freedom of movement, right?
Right. Up, down, left, right.
Exactly. And 1 dimension of time where we are dragged relentlessly forward.
Yeah.
But what you are describing is a regime where those fundamental architectures of reality actually swap roles.
And that regime is exactly what we are dissecting today on this deep dive. So welcome.
It's great to be here.
Today, for you listening, we are pulling from a massive stack of astrophysics research, papers on general relativity, and some deeply unsettling quantum mechanics theory.
Very unsettling.
Yeah. And our mission today is to strip away all those pop culture exaggerations. The sci-fi tropes of cosmic vacuum cleaners and glowing wormholes.
We want to get away from the movie monsters.
Exactly. We are looking at black holes, but we're looking at them as profound, very real physics phenomena that fundamentally break our current models of the universe. And I want to assure you, the listener, you do not need a science degree for this. We are going to take our time and unpack this together.
The breaking of those models is actually what makes them so incredibly valuable to physicists. I mean, black holes aren't just destructive phenomena. They are the ultimate stress test for our equations.
Because when you want to find out where a theory is flawed, you push it to its absolute limits.
Right. And there is literally no environment in the universe more extreme than the interior of a black hole.
Okay, let's unpack this. Because even the very name, black hole, is doing a lot of misleading work right out of the gate.
It's a terrible name, honestly.
Right. It makes you think of an empty pit. Or like a literal hole in the ground. But it's not a hole at all. It's not even a traditional object like a planet or a star, is it?
Not at all. To really grasp this deep dive, we first have to discard our everyday definitions of objects and places. A black hole is actually a region of space where matter has been extraordinarily compressed.
A region of space. Okay. So to truly understand how weird this compressed region is, we have to look at the invisible line that defines it.
The event horizon.
Yes, the event horizon. We throw that term around a lot, but I really want to get into the mechanical physics of what it actually represents. Because what makes a black hole is that the gravity in this region is inescapable.
That is the defining feature, yeah.
And the common definition usually brings up escape velocity. So escape velocity is basically the speed you need to go to break free from something's gravity, right?
Exactly.
Yeah.
On Earth, you just need a big enough rocket.
Right. You burn enough fuel, you hit about 11 kilometers per second, and you can leave the Earth. But for a black hole, the escape velocity exceeds the speed of light.
Which is the crucial detail. Because, as Einstein showed us, nothing in the universe can travel faster than light.
Absolutely nothing.
Nothing. Not matter, not light, not even information.
Mm-hmm.
So if the required speed to leave this region is faster than light, absolutely nothing gets out.
So the event horizon is just the boundary of this inescapable region.
Yep.
But I want to clarify what this boundary actually feels like, because sci-fi always makes it look like a shimmering force field or a solid wall of energy.
Yeah, the movies always get that wrong.
Right, but if you drifted across it, you wouldn't feel a bump. There's no wall.
No wall at all. What's fascinating here is how space-time itself bends. Inside the horizon, space and time are so severely warped that away from the center ceases to be a direction you can travel.
Which brings us to this analogy from our source material that I absolutely love. It's the next Tuesday analogy.
It's a perfect way to visualize it.
Yeah, because once you cross that line, the center of the black hole is no longer a physical place in space, right?
Mm-hmm.
It mathematically becomes a moment in your future.
Exactly. You can no more avoid moving toward the center than you can avoid next Tuesday arriving.
Wow. Next Tuesday's coming no matter what you do. You could fire your rocket thrusters with all the fuel in the universe trying to fly away, but you're just moving toward next Tuesday.
In fact, firing your engines might even get you to next Tuesday faster, depending on how you do it, because of how time dilation works.
That is deeply unsettling. So if a black hole is just this region of severely bent space and time, how does the universe actually go about making one?
Well, to build something that extreme, you have to look at the life cycle of massive stars.
Okay, section 2, birth, death, and cosmic scales. Let's talk about the stellar standoff.
The stellar standoff, I like that. I mean, we look at stars and see these peaceful, glowing orbs, but break down the life of a star, and it's really a billion-year standoff between two titanic forces.
Okay, what are the forces?
On one side, you have gravity. The sheer mass of the star is relentlessly trying to crush all of its matter
It's
inward.
constantly pulling everything toward the center.
Exactly.
Yeah.
And on the other side, you have nuclear fusion.
Hmm.
Deep in the core, atoms are smashing together, creating an unbelievable amount of energy that pushes outward.
So gravity pushes in, fusion pushes out.
Right. And as long as the star has fuel for fusion, those two forces balance perfectly.
But the fuel isn't infinite.
No, it's not. And when the fuel for fusion finally runs out, that outward push just instantly vanishes.
It just turns off.
Yep. And gravity, which has been waiting for millions of years, definitively wins. The core of the star collapses in on itself at a significant fraction of the speed of light.
Which leads to a supernova, right? I mean, for the listener, a supernova is when the outer layers of the star detonate outward in literally one of the brightest events in the universe.
It's incredibly violent. The outside explodes, while the inside crushes down.
And if that collapsing core is heavy enough, it crushes all the way down into a black hole.
Right. Though, I should note, if the core is slightly lighter, it halts before becoming a black hole and becomes a neutron star, which is an equally strange, extremely dense leftover.
Right, but for our deep dive today, we're talking about the cores that are too heavy to stop. They just keep collapsing. So this is how we get stellar mass black holes.
Yes. They are formed from dying stars, and they usually weigh anywhere from 5 to maybe a few dozen times the mass of our sun.
Okay, so that's one size. But our sources point out that black holes come in vastly different sizes. There are also supermassive black holes.
Oh, yes. The scale difference is hard to even wrap your mind around. Supermassive black holes can be millions to billions of solar masses, and they sit right at the centers of galaxies.
Including our own, right? Our Milky Way galaxy has one.
We do. It's called Sagittarius A star, and it weighs about 4 million times the mass of our sun.
4 million suns just lurking in the center of our galaxy. But wait, if stellar mass black holes come from dead stars, how do we get a black hole that weighs 4 million suns?
That is a genuine scientific mystery. It's actually an open question in astrophysics today. We know perfectly well how stellar mass black holes form. But how supermassive ones got so big, we aren't entirely sure.
Huh. So what are the theories?
Well, they might have grown slowly over billions of years,
Yeah.
just swallowing up gas and merging with other black holes.
Okay, like building blocks.
Right. But another theory suggests they might have formed huge right from the start, from the collapse of enormous pristine gas clouds in the very early universe, completely bypassing the star face.
Wow, just directly collapsing into massive black holes.
Yeah, direct collapse. It's a fascinating area of research.
It really is. But, hearing that a 4 million sun black hole is lurking in our galaxy usually triggers panic for people. Which leads us to the biggest myth we need to bust today on this deep dive.
I know exactly the myth you're talking about. The cosmic vacuum cleaner.
Yes, the cosmic vacuum cleaner.
Yeah.
People think black holes roam around space just aggressively sucking things up.
They absolutely do not.
So what does this all mean for us? Let's use that thought experiment from the source material. I think it perfectly illustrates the point. What if we magically replaced our sun right now with a black hole of the exact same mass?
It's a great thought experiment. If we swapped our one solar mass sun for a one solar mass black hole, Earth's orbit would not change one bit.
Wait, not one bit. We wouldn't get sucked in?
Nope. We wouldn't get sucked in. Now, to be fair, we would quickly freeze to death because we wouldn't have the sun's light and heat anymore.
Right, the lights would go out. That would be bad.
Very bad. But gravitationally, we would confidently keep orbiting on the exact same path.
Because the rule of gravity behaves exactly the same way for a black hole as it does for anything else.
Exactly. Gravity depends only on two things, mass and distance. And since neither the mass of the center object nor our distance from it changed in our thought experiment, the gravitational pull doesn't change at all.
Here's where it gets really interesting to me, though. If a black hole doesn't pull any harder than a star, what makes them dangerous? Because they are dangerous, right?
Oh, absolutely. But what makes them dangerous isn't that their gravity reaches out further. It's that their mass is incredibly concentrated.
Concentrated, right.
Because they're so small and dense, you can get much, much closer to their center than you ever could to a normal star.
Because with a star, you just bump into the surface.
Exactly. But a black hole has no solid surface to bump into.
Yeah.
You can get insanely close to the center of mass, And that is when gravity gets dangerously strong.
Okay, so what actually happens if you make the mistake of flying directly at one and getting too close to that concentrated mass? Let's take the journey inward.
The journey inward, this is where things get a bit gruesome.
Right. We need to talk about tidal forces because gravity gets weaker the further away you are from an object.
Right. And it gets stronger the closer you get.
So, to define a tidal force for you listening, if you fall feet first toward a stellar mass black hole, your feet are meaningfully closer to the center of the black hole than your head is.
Yes, by about, 5 or 6 feet, depending on how tall you are.
Right. And because you are so incredibly close to the concentrated mass, the pull on your feet is overwhelmingly stronger than the pull on your head.
Massively stronger.
And the result of that is spaghettification.
Spaghettification. It's a real technical term. You would be stretched lengthways and squeezed sideways into a very long, very thin stream of matter.
It sounds incredibly undignified and fatal.
Highly fatal.
Yeah.
But crucially, for a small, stellar mass black hole, this violent stretching death happens before you even reach the event horizon.
Wait, really? Before you even cross the line?
Yeah. The tidal forces outside a small black hole are so severe that you're torn apart in normal space. You never even see the inside.
That is wild. Okay, so a small black hole kills you outside the front door. But wait, what does a supermassive black hole do? Because that must be a billion times worse, right?
This is the counterintuitive twist. A supermassive black hole is actually much safer to cross.
Safer? How is a giant black hole safer?
Because it is so massive, its event horizon is pushed enormously far out from its center. We're talking millions or billions of miles away from the singularity.
Oh, I see.
So when you cross that boundary, you were still incredibly far away from the center. The difference in gravity between your head and your feet at that massive boundary is quite mild.
So no spaghettification at the event horizon?
None at all. You could sail right across the event horizon in perfect comfort. No alarms would go off. There'd be no sign you crossed it.
Just smooth sailing.
Smooth sailing. But, and this brings us back to section 1, even though it was comfortable, your fate is entirely sealed.
Because the center is now your future.
Exactly. You just have a finite amount of time drifting inside before the tidal forces deeper in finally catch up and finish you off.
That is profound dread right there, just comfortably waiting for next Tuesday. So that's what you would experience if you fell in. But what if a friend was watching you fall in from a safe distance?
Now we get to the observer, the clock, and relativity.
General relativity. Because Einstein taught us that gravity slows time.
He did. And this is a very real effect.
And to prove this isn't just theoretical math for you listening, I want to bring up everyday life. We use GPS satellites all the time, right?
Every single day.
And because those satellites are up in orbit, they are further away from Earth's gravity than we are on the ground.
Right. The gravity is slightly weaker up there.
Which means their clocks actually tick at a slightly different rate than our clocks down here.
Exactly. Time runs a tiny bit faster for the satellites. And if our software didn't mathematically correct for this time difference, our satellite navigation would drift by kilometers every single day.
Your phone's map would just become useless within hours.
Totally useless.
Yeah.
So time dilation is a proven fact.
Okay, so scale that up. If a planet's gravity alters time a tiny bit, what happens to time at the edge of a black hole?
Near a black hole, this time-slowing effect becomes absolutely enormous.
So let's go back to the friend watching me fall in. I'm falling toward a supermassive black hole. What does my friend see?
If your friend is watching you from a safe distance, they're going to see your movements start to drag out. You'll seem to slow down.
Like slow motion.
Yeah, extreme slow motion. And the light bouncing off your ship actually stretches out to the red end of the light spectrum.
It gets redder and dimmer.
Yes. To your friend, you appear to completely freeze at the boundary of the event horizon. You freeze, you turn red, and you slowly fade away. From their perspective, you never actually cross into the hole.
I just get stuck there forever. But from my perspective...
From your perspective, looking at your own watch, you fall in and cross the boundary in a perfectly ordinary amount of time. You don't feel slow at all.
Wait, so my friend sees me frozen outside forever, but I experience falling inside. Who is right?
If we connect this to the bigger picture of physics, both perspectives are 100% correct.
How can they both be correct? That doesn't make sense.
It's because there is no universal clock that arbitrates between the two of you. Reality in physics is entirely dependent on the observer.
Wow. Bending time, freezing reality, stretching light. I mean, this all sounds like completely abstract mathematics. And actually, for decades, even Albert Einstein doubted that black holes existed in nature. Right.
He did. He thought they were just a mathematical quirk in his equations that the real universe wouldn't actually allow to form.
So how do we know black holes are real? How do we get the receipts?
Well, this is how science builds confidence. We look for completely independent lines of evidence all agreeing with one another. And we have three major pillars of evidence now.
Let's go through the three pillars. Evidence number one, invisible orbits.
Right. So astronomers spent years looking at the very center of our galaxy, and they track individual stars whipping around an apparently empty point in space,
Just orbiting nothing.
orbiting what looked like nothing. But based on the incredible speed of those star orbits, the math proved there had to be 4 million suns worth of mass crammed into a region smaller than our solar system.
And only a black hole fits that math. You can't put 4 million normal stars in a space that small. They'd just collide.
Exactly. And that specific discovery was so ironclad, it won a Nobel Prize.
Incredible. Okay, evidence number two, gravitational waves. This happened back in 2015.
Yes. Detectors on Earth, these massive, highly sensitive instruments, picked up actual ripples in the fabric of space-time itself.
Ripples in space.
Yes. Two black holes had spiraled into each other and merged over 1 billion light years away, and that collision sent shock waves through the universe. When those waves washed over Earth, our detectors felt the stretch and squeeze of space, and the signal matched our theoretical predictions perfectly.
Which is just mind-blowing. We literally felt them crash. But human beings are visual creatures.
Which brings us to evidence number 3, direct images.
2019, the Event Horizon Telescope.
Right. They captured actual images of the supermassive black holes in the galaxy M87 and our very own Sagittarius A star. But I have to ask an obvious question on behalf of a listener here.
Go ahead.
Wait, if absolutely no light can escape a black hole, how do you take a picture of it? It's a great question. The trick is, you don't actually photograph the hole itself. You photograph the furiously glowing gas swirling right around it.
Oh, the stuff waiting to fall in.
Exactly. The accretion disk. It's superheated and glowing brightly. So what you see in the image is this bright ring of light, and the black hole is the dark, circular void, the shadow, right in the very center.
The silhouette of the black hole against the glowing gas.
Exactly.
Okay, so we have the receipts. We know they're out there, and we know they trap absolutely everything that falls in. But does a black hole last forever?
Now we are getting to the really cutting-edge stuff.
Section 7, Hawking radiation and the ultimate paradox.
Right. So in the 1970s, Stephen Hawking proved that black holes aren't perfectly black.
They leak.
They leak because of extremely complex quantum effects happening right at the microscopic edge of the event horizon. Black holes very, very slowly leak energy back into space.
And this is what we call Hawking radiation.
Yes. And the consequence of this radiation is that black holes evaporate.
They evaporate like a puddle of water.
Basically. It happens incredibly slowly. I mean, a stellar mass black hole takes vastly longer than the current age of the universe to disappear. Yeah. But in principle, given enough time, they eventually vanish completely.
Okay, so this gives me a huge aha moment. If the black hole eventually evaporates and vanishes, what happens to all the stuff that fell in?
And there it is. You just hit on the information paradox.
The information paradox.
It is arguably one of the deepest unresolved conflicts in modern physics today.
Because it creates a clash of our best theories. Right?
A fatal clash. So you have quantum mechanics, which is the physics of the very small, and quantum mechanics insists that information about the universe, the exact quantum makeup of particles, can never, ever be destroyed.
It's a fundamental rule. Information must be preserved.
Always. But then you have general relativity, the physics of the very large, which describes black holes. And relativity seems to say that once stuff falls into a black hole, and then that black hole evaporates via random Hawking radiation, that information is gone forever.
Erased from the universe.
Erased. Okay. Completely destroyed.
So quantum mechanics says it can't be destroyed, and general relativity says it absolutely is destroyed.
That is the fault line. Black holes are the exact place where our two best, most successful scientific theories fatally contradict each other.
They cannot both be right.
They can't. And that is why black holes are so important. They are the ultimate laboratory where the next grand theory of physics, whatever replaces or unites these two theories, will have to prove itself.
Wow. We have really covered some ground today. I mean, we've gone from the death of massive stars to regions of space where time literally freezes.
We dispelled the myth of the cosmic vacuum cleaner.
Right. Earth would be fine orbiting a black hole sun. Cold, but fine. And we've arrived at the very limits of human understanding with the information paradox. For you listening, it's incredible to think that black holes, these things defined entirely by what they trap, or ironically, our greatest teachers about how the universe actually works.
They force us to confront what we don't know.
They really do. And before we go, I want to leave you, the listener, with a final provocative thought drawn from this paradox. Think about that contradiction at the very edge of a dying, evaporating black hole.
The moment of truth?
Exactly.
The
When the universe finally forces our hand and humanity manages to resolve the information paradox, which of our sacred laws will we have to rewrite?
a profound question.
Will we have to completely change our understanding of gravity and space, or will we have to shatter the rules of quantum mechanics and accept that the universe deletes its own history? One of them has to give.
Something have to break.
Thank you so much for taking this deep dive with us today.